Okay, so previously, what we showed in the last video was this reduction of an aldose. So we had this aldose structure, an aldehyde functional group up here at the top, and this was a sugar that we called D-mannose. And by throwing in sodium borohydride and acid, simply what we did is that we added a hydrogen onto the carbon and a hydrogen onto the oxygen. Mechanism is a little bit different than that, but overall that's kind of how you maybe want to think about this reaction in the simplest terms. So hydrogen goes onto the carbon, hydrogen goes onto the oxygen, and that ended up with a CH2OH group up here at the top. We said this wasn't an aldose anymore because we don't really have a sugar here. So what we do have, however, is what was an aldehyde converted to an alcohol, and we called this an alditol because of that. And I said that, well, in the next video, meaning this one, we're going to take a look at what happens to a ketose. So here we have a ketose. Here is the ketone functional group, right? And it's this ketone functional group now that's going to be reduced by the sodium borohydride. And I said it's going to take me about longer than 4 minutes to explain what happens here because there's a choice of what happens here. Alright, so basically, overall, the same type of thing happens. We have a CH2OH group here at the top. Then down below we have a CH2OH group. This double bond, we have a hydrogen and an OH, and we have an OH and a hydrogen, and we have an OH and a hydrogen. Okay, so in this reaction, nothing really different happens. The double bond breaks just like it did with the aldose, and a hydrogen goes on to that oxygen, and a hydrogen also adds on to the carbon. So look at there. Look at what we've got. So this is something very similar as what we saw before. Now, that wasn't our only choice. We chose to do that because our oxygen was already drawn to the right-hand side. And because that oxygen was already there, it was kind of easier for us to do that. But we have a choice. We can actually get two different structures here from the reduction of a ketose. And how do I get two different structures? Well, CH2OH is still up at the top. CH2OH down here below. We do a double bond here. OH to the right, or to the left. OH here to the right. And OH here to the right. Okay, so in the other version, if I add NABH4 and H3O+, I do have a second option, and what happens is that this double bond breaks to a single, but that oxygen can switch sides. H still adds on to the oxygen, H still adds on to the side with carbon. The only difference is that, again, these are kind of like C2 epimers. When this double bond breaks, those OH groups can go to the left hand or to the right hand. We're seeing that to be a very common trend with these reactions, right? So with the ketose, I get two different options. OH could stay where it is, typically maybe on the right-hand side, or that OH group could go to the left-hand side. And this forms two different structures for us, really, versus the aldose form. The aldose form up here at the top, well, this is not really a chiral carbon, is it? I mean, this carbon has two hydrogens on it now, so it really doesn't matter. I only get one option with the aldose form. The ketose form, however, I get two options with. So I'm just going to put that in the side note down here at the bottom. For the reduction reactions, the aldoses give me one structure, right? There's only one type of structure because that carbon at the top that it has broke that carbonyl bond with, that is no longer a chiral carbon anymore. So I only get one structure there. That's it. CH2OH at the top, and you call it a day. However, if this is a ketose, you will end up getting two structures. And that's because this carbon that's involved in the double bond, that carbon is chiral. So when the OH and the H form on that carbon, and that's what we're seeing here, this is a chiral carbon, which means stereochemistry is very important. I could see OH to the left, or I could see OH to the right. And that is the key with the reduction reactions. Aldoses give me one structure, ketoses give me two structures. So what do we call these structures? I mean, if we come up here to above and we take a look at what these structures are kind of called, we said we started off with the aldehyde, that got converted to an alcohol group, and that we called the alditol structure. Well, what do we call these? Do we call these the ketotol structures because they came from a ketone? And the answer is no. We actually do call these alditols as well. I'd like to start off mentioning how alditol maybe is used as far as the name goes, because it kind of makes sense in the beginning. But with the ketones or the ketoses, well, these ketoses, we can't really distinguish whether or not they came from an aldehyde or a ketone if Mother Nature makes them. So really the term alditol is very general. An alditol is basically a polyalcohol. That is really all that this is, a polyalcohol. I like to mention the word al because we kind of start off learning alditol structures with aldehyde functional groups, so that's kind of why they bring that name into the picture. But all that alditols are polyalcohols. Look at this. This carbon has an OH. This carbon has an OH. That carbon has an OH. This carbon has an OH. That carbon has an OH. So no difference at all, period. Now, we said that this was D-mannitol. So this structure up here is D-mannitol. And D-mannitol is very common. If you like mushrooms, if you like onions, D-mannitol is found in a very high concentration, especially in a mushroom and an onion. Okay, well, down here below, this sugar, if I look this sugar up in the chart, CH2OH, carbonyl on the second carbon, and then my OH goes left, right, right. This is D-fructose. D-fructose, of course, is kind of the sugar that's found in fruit. We've mentioned this before as well. Okay, so if I look at this structure, I need to find this structure that has the OH group here on the right, and then the left, and then the right, and then the right. And when I do that, and I find this structure on the chart, this is going to be called glucose. But it's not really a glucose, is it? There's no C double bond O up here at the top. So because of that, this is an alditol. We don't call it glucose, we call it glucatol because of that. Well, the other version over here to the left is a structure that has the OH left-handed, left-handed, right-handed, right-handed. If I try to find this in the chart, I'm going to see that this is called mannose. Well, it's not really mannose, is it? Because I don't really have the aldehyde functional group up here at the top, so this is called D-mannitol. The same structure that we had up here at the top. So basically what we're saying is that D-fructose, which is the sugar found in common fruits, can be converted into a alditol that is very commonly found in mushrooms and onions, right? It's kind of weird when you think about it that way. Very, very strange. D-glucatol, on the other hand, is also called sorbitol. S-O-R-B-I-T-O-L. Sorbitol is a different alternative for a sweetener. It's actually 60% as sweet as sucrose. So this compound is very commonly found in cherries and any type of berry. So we get fructose that can be converted into something found in mushrooms and onions, and we also get fructose that can be converted into something that's found in things like cherries and plums and pears. So again, very, very strange because we kind of relate those to two different backgrounds on us. Sorbitol is used as a sugar substitute, especially these companies that make artificial sweeteners or these companies that make candy. If they don't really want to use pure sugar, then they can use sorbitol to kind of replace that because it is very sweet on the tongue. And you know us, we love sweet things. Again, like I've said before, if it tastes good, it's bad for us. If it tastes bad, it's good for us. Sugar, sorbitol, is very, very sweet. So in high concentrations, it's probably bad for us. We want to stay away from it, but it is still a sugar substitute. So maybe a little bit better than sugar as a whole. Those studies are still out there, but it gives us a debatable point at least to talk about. So that's the story with reduction. Reducing aldehydes, reducing ketones. Just keep in mind that when you reduce an aldose, you get one structure. When you reduce a ketose, you end up getting two structures. So in the next video, we're going to be looking at oxidation now, the sister counterpart. So what is oxidation? How can we oxidize the sugars? And what does that really mean?